Okay, so welcome everyone to the second lecture on this. I thought maybe we should sort of begin where we left off yesterday about the stoichiometric subspace. Okay, so let me go through that a bit, and then we'll continue. So basically, this reaction that we've been talking about, our favorite enzyme kinetics, which is up there with all the rate constants. Okay, so if for that, okay, let's try to just go through the stoichiometric subspace argument, because that's an important quantity that we need to calculate other things. Okay, so and here on this side, just to save some time, I've written also our A and Y matrix. So in the tutorial today, let's just try writing this A and Y for some bunch of stuff and writing the equation, the rate equations down, etc. Okay. Actually, in this particular case, as we'll do in the tutorial today, we can actually solve the rate equations too without much fuss, without doing all this business. But let's try to solve them, and then we'll see how using some of the structure that's lying behind it, we can actually solve it even easier when we understand the structure. Okay, so let's get back to our stoichiometric subspace, and let's hope that this pen is a bit darker than the other ones. So basically the idea was the following, and I know many of you had some questions about it yesterday. So let's look at our reaction again. E plus S goes to ES goes to E plus P, and E goes to phi goes to S, with all our K's and K bars and everything. And of course, if we can do it here, we can do it anywhere. Okay, so this is just an example. So how many reactions are there? There's some reaction for, there's a reaction going this way. This is a completely reversible network, right? So in our definition of reversibility. So there's a reaction going this way and a reaction going that way. Okay, so that's 2. And a reaction going this way and a reaction going that way, 4. So 6 and 8. So there are 8 reactions. Now for every reaction, you can take this, you can, remember how I said that, the species can be thought of as a vector, a column vector. There are 4 species in this problem, 4 species, which are E, S, ES, and P. Right, so 4 species, and so we can have a column vector with 4 rows. And a 1 in each row in the appropriate place defines for you the species. And in the very same language, we can also denote a complex, right? So now that we have our column vectors, E plus S is just the addition of our vectors E and S, right? And ES is both a species and a complex. E plus P is just the addition of E and P, etc. So, and of course, if there was, for example, A plus A, then there would be a 2. So if there was a complex 2A or 3A, etc., there would be a 2 or a 3 in the appropriate place. Okay, so if we have this set of species, okay, and a complex is just denoted by E plus S. Every reaction you can think of as, summing these vectors or subtracting these vectors. So E plus S goes to ES would be a reaction vector 1, minus 1, minus 1, 1, 0. Right? So this is E plus S goes to ES. And now if I write that, I don't need to write ES going to E plus S, because ES going to E plus S is, of course, just the minus of this. 1, 1, minus 1, 0. Okay, yeah, and my sort of notation just now is that this denotes E, this denotes S, this denotes ES, this denotes P. Okay, just as we were doing yesterday. So, okay, I'm trying to not block your view here. So basically, it's just as simple as that. I'm just adding and subtracting. And And we didn't need to worry about that, just because the quantity we are going to be interested in is going to be the number of independent such vectors. And this is not independent of this. This is just -1 times that, right? So if we just follow this sort of rule all the way through, then what we see is that our independent vectors just correspond to one of, so it's enough if I take a pair, one of this 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 pair, in this particular example. Okay, so and then I get, if I take one of this pair, I get, let's say I always just take the one going this way. Okay, just to be a bit clear. Then I lost the ES and I gained the E and the P. And in this particular case, I went that way, so I lost the E, and that was about it. And this way I gained an S, and that was about it. Okay, so please keep track that I'm not making any mistakes on the board. So these were the four independent. These were the four independent column vectors. And it's not necessarily, so what's the, and in this, okay, so let me say this and then I'll say the caveats. Okay, so in this particular case, these are the four independent column vectors. So now if we define our S, our stoichiometric subspace, this quantity S, as the span of the stoichiometric subspace. Okay, and so in the maths notation, it people write it like this: span. Let me see. Yes, you're still able to see this. These are our. We take all the reactions that are in our network, and we construct these reaction vectors. And this S is the span of this. So this is the definition of this. And span is a fancy way, I guess, of saying that it's the number of independent vectors that you can construct. Okay, so that's so I said I'll show you a formal definition. That's a formal definition of this S that we will need to construct this quantity of interest called deficiency. So in this particular case, it was 4. It of course so the caveats are that it doesn't have to be, clearly the number of reactions plays a role in what the span of this is, but it doesn't have to be equal to the number of reactions. We saw an example yesterday when I could with periodic boundary conditions, and we'll see another example. It doesn't have to be equal to the number of species. Okay. But think a little bit, can it be more than the number of species or not? Okay, so there are some constraints on it because it's what it is, right? It's a reaction vector, but it doesn't have to be equal to the number of species. It doesn't have to be equal to the number of reactions, etc. But it's a very easy quantity. Once we know what it means, it's an easy quantity to work out. Okay. So one example that we might do in our tutorial today would be, for example, that you just take this, just take the top reaction here. So we just take the top reaction. And if we take the top reaction, we just have, so what would the span be, for example, in this particular case? Remember, the span is the number, okay? So you don't have to tell me what the vectors are. What would the span be here? It would just be 2, right? Just 2. Because this is one vector, that's one other vector. They are independent of each other. That's all that there is. So the span is 2. But the species space is 4. So what's going on here? So what does the species space mean? So it's the space, on which my dynamics can move around, right? So if I'm talking of species numbers, probabilities, or I'm talking of concentrations or fractions or whatever, and I'm talking of time evolutions of those quantities, that four-dimensional space is where that thing can move around. But now what I'm saying is that it can move around actually only in this two-dimensional space. Why? Okay, why? Because there are two conserved quantities in this reaction. So it's easy for you, it's easy to see. And we can, we'll take an example of this in our tutorial as well. We'll just set up all the equations and try to work them out. Okay, and you'll see how the conserved quantities play a role. It's going to be important even when we talk of the stochastic variation. So the conserved quantities in this particular case, any guesses? So see, look at how these reactions are taking place. We have XE, remember X is our concentration. So XE plus X, ES is the constant. Right, every time I produce a E, I eliminate an ES, or every time I eliminate an E, I produce an ES, right? That constant was not there in this one, precisely because of this reaction, this phi business, okay? There's a source and a sink, so, there's no conservation of E there. And there's yet another one here, and that is X, let's see, XS plus XES plus XP. Okay, like yesterday, just, stop me anytime, ask me questions or clarifications or whatever, okay? It's just more fun when it's a bit more interactive. So these are these two conserved quantities here. And there's a mathematical way to see this also, because if I now write down the reaction vectors, right? So the first hint that there are conserved quantities is when I look at my reaction network, see how many species there are, and then I count the dimension, the stoichiometric subspace, the span of the stoichiometric subspace, and I see that it's less than the number of species. Then that immediately gives me a clue that there are conserved quantities. And in fact, it tells me even how many. Then it's only a question of finding those conserved quantities. And then you can even check that, mathematically that that's the case, because if I write the reaction vectors here, so the reaction vectors, that's how I calculated the span, right? So the reaction vectors here are, let's say, I just take one direction, the same two that I wrote down last time, this one and this one. ES goes to -1. Sorry. These are our only two independent vectors that we could construct out of that reaction system, right? So, but now if I just look at this gives me two vectors also. So one gives me a vector. There's nothing on the other side, so nothing to subtract. So it's just E. I'm writing it as a row vector for a reason that you'll see. Let's see, E, F, and nothing. And then the two is, let's see, S. No, there's no E here. There's an S, there is an ES, and there's a P. Okay, let's see. So hopefully I've not made a mistake here. And you can see that these are sort of, each of them is orthogonal to each of those two. Right? Right? So basically, the dynamics is moving around in a space that's less, more constrained than the full species space. Okay, so that's how. So that's why the stoichiometric subspace is important, and you can even just see it sort of pictorially. Okay, I hope I can erase that. Yes.
Yeah, ma'am, in first constraint, you have not taken the S species. I mean, why so? So the equation is E plus S. It's going to ES.
This one you mean?
Yeah. Yeah. So here, why don't we take the concentration of S species as well? I mean, to write the constraint. So,
so
can you
it's just
explain
that
this
there are.
equation? Yeah.
So I guess I'm just writing it as, two separate constants. Two, I mean, because I'm writing it as like, so each of these reactions keeps both these constant, right?
Yeah, right. But I mean, the first equation reads like E species plus S species. That is going to ES. I mean, so the concentration of S species should matter in writing the constraint in first equation. That's my question. I mean, why we have
So
written
the
X?
concentration of X will, of course, play a role in the reaction itself, right? But when the reaction has taken place, sure, S reduced also. But if you look at E and ES, those two, I mean, if I count just the numbers of E and ES in my system, that reaction is keeping it a constant.
Yeah. Okay.
Sure. So S reduced, of course, but then S is obeying a separate conservation law out here.
Yeah. Okay. Thanks.
So basically, the idea is you should be able to sort of pick out, because now we got a clue, right? Our species space was 4, our stoichiometric subspace span is 2. So that means there are 2 conservation laws, and so then we need somehow to figure out what these conservation laws are, and these are 2, for example, and they'll be important for us. Okay, so it's good to keep these things in mind. It's kind of very automatic, since this is a very easy thing to compute. Okay. Yeah. Great. So we can also do. Yes. Yeah.
No. So if I know the reaction vectors, then if I can find some orthogonal vectors which are positive, then I know the conserved quantities.
Right.
So if there were if you had the 2 equations, then I guess because of the phi, you said there are no conserved quantities, right?
In this case. Yeah. Because remember. Yeah.
Oh, sorry. You still have 4 of these reaction vectors, but it's not obvious that you can't find such a orthogonal vector. I mean.
Yeah. So it's not obvious, but you can't, I guess.
Okay.
In the sense that because because you see the play that you have is that 4D space in some sense, and those reaction vectors are spanning that 4D space. So maybe there's a more
so if there are no source and sink terms, then is it true that this stoichiometry number always gives you the number of conserved quantities? Or not
what do you mean? So you mean this number?
Yeah.
I mean, I could have a source and sink term here. So for example, I could have a case where let's just see. For example, I can just say S. I can consider reaction network S goes to 0. I mean phi.
But it's still conserved.
But now the stoichiometric becomes what? It becomes 3.
3, okay.
And there is 1 conserved quantity.
Oh, okay.
This will not be conserved. Okay.
Okay. So the conserved quantity one just has to find by some different method.
Yeah. Okay. What exactly it is, you find by some different method.
Right.
Yeah.
Okay.
Maybe there's a better way to do it too. I don't know. It's worth thinking.
Can't we just say that it's the dimension of the space minus S?
The perpendicular space or something.
Yeah.
There is a mathematical word for it that I've forgotten. I should know actually, because we will use that stuff. So there is a space, and then there is a sort of okay. So there is a space where your vectors are living, and then there's another space which is sort of which have the vectors all perpendicular to this one, like orthogonal to this one. Orthogonal subspace. Yes. Now I remember. So the conserved quantities are living in the orthogonal subspace. Okay.
Yeah.
Yeah, nice. So let's see. So, oh yeah, I was going to tell you what the, yeah, so you can look at it pictorially also, right? Because conserved quantity, all that it means is that, I have my species, so this is my, so suppose I have some X A and XB or something like that. Okay, two species. And they are going to obey some chemical reaction. Okay, so think a little bit about what chemical reaction it could be. If XA plus XB is constant, it doesn't have to be, I mean, not necessarily unique, but a typical chemical reaction that gives me XA plus XB is constant, which means that the dynamic will move around in some up and down a line like that, right? So I have my 2D space to live in, but because of my conservation law, I'm constrained to a lower dimension. Similarly, if I have, so that's just, the subspace idea. So why stoichiometric subspace? It can be a subspace. It could be the whole space, species space. So for example, I could, yeah, this is not a good drawing, but you see what I mean. If I have 3 species, XA, XB, XC, then I would be, can you see that? Yeah. So if I am, constrained by some conservation law like that, then, I am forced to remain in that plane, or, so just pictorially what it means. So this could be a chemical reaction that goes like this. This could be a chemical reaction that goes like this. Okay. So that was our stoichiometric subspace, because I felt maybe that we didn't get time to discuss it yesterday. And the reason that we were interested in that was because we could then calculate this very interesting quantity, which is called deficiency. Okay, I mean, so I'll show you a picture on the slides shortly, but it's a very easy quantity in some sense to calculate, right? So this deficiency is the number of complexes. Okay, so if one has to be very careful, then this is, a set C, and then this is the number. But then I'll become a little bit more careless and just call it C. Okay, so, but just for the first time at least, let's be a bit correct about this. It's the number of complexes minus the number of linkage classes minus this stoichiometric span of the stoichiometric subspace. So it's given any network, even a very big one, this is actually not a difficult quantity to calculate at all. It's some counting thing, right? So C is the number of classes, L is the number of linkage classes. Sorry, C is the number of complexes, L is the number of linkage classes, S is our dimension of stoichiometric subspace. And as I said yesterday, we'll see that this has to be strictly non-negative. It means like it could be 0, of course. That's the case you're going to consider, where there's a lot of help that we get from this hidden structure. And then it could be non-zero. Okay, so in some sense, the 0 case is the case where we can solve everything. And you might think it's a little bit of a boring case, but just understanding the structure is very interesting, I think. The 0 case, as we saw from the deficiency 0 theorem, implies there are unique fixed points or unique steady states. And we'll even see that it implies that steady states are factorized, which is very interesting. Okay. On the other hand, the non-zero deficiency case might be everything else, like cases where you have multiple fixed points or extinction events or limit cycles or, all possible other things. And not much is known when you have deficiency non-zero, but a lot is known when you have deficiency zero. Okay. So as you see, it seems a bit mysterious. How can something like this affect anything at all? Okay, so that's what we're going to try to understand. But let's do a few examples first, just so that we know that we understand this really well. So for example, so we already have a couple of examples here. Our enzyme kinetic network. Let's see, if I write here, you can still see it. What is the deficiency? Here, 6 complexes, 2 linkage classes, and 6 complexes, 2 linkage classes, and 4, so 0. Let's see. Okay, that's a bit, yeah, it's barely legible, so I won't go to that side of the board. Okay, what about this one? We have 5 complexes, 2 linkage classes, but we said that the stoichiometric subspace became 3, so deficiency is again 0 there. Okay, so let's run through a few more examples, just simple ones. We'll also look at our zero range process. How many complexes?
2.
Yeah, 2. How many linkage classes?
1.
1. And then the stoichiometric subspace business?
That's 1.
Yeah, exactly. So in this case, easy to see. Only one reaction. So that whatever we get is we get for that, right? So that's 0. Okay. What about something like this? Same case, right? Everything is the same. Deficiency is again 0. Let's take another example. So you have to be a bit careful when you calculate this. Maybe I will write this here. Delta equal to, okay, so now I'll start becoming a bit careless, and this will be the number of complexes, number of linkage classes, and our stoichiometric subspace. Okay, so what if I have a chemical reaction network that looks like this? How many complexes?
5. Oh, sorry, it's 4.
4, really? This one is the same as that one, remember?
Oh, right. I'm sorry. Yeah, it's 3.
Yeah, great. So that's exactly why I wanted to say how you should be careful, how to do this, because I can write my chemical reaction network as I want, right? So I still have to do the counting correctly. How many linkage classes?
2.
No. So you see, I wrote it in a way that it looks like 2, but actually, you see, I can write it like this too. So I can I can write it like this. Right?
Yeah, right. Yeah.
So you see that it's one connected component, really. So it's really only one linkage class. So I am free to write my chemical reaction as any way I choose, but I should be careful how I identify my complexes and linkage classes. Okay, linkage class really means I'm thinking of it like a graph. Those complexes are nodes in the graph. And then I'm really trying to understand the number of connected components, distinct connected components, right? So L is just 1 here. And I suppose if you check out the stoichiometric subspace, you'll see 2. Okay, this gives you 1 independent vector, another 1, but this will be a sum of the other 2. Is this reversible or weakly reversible? Or neither?
It's weakly reversible.
Right. Great. So it's actually weakly reversible because remember our definition. All these things are important because when we talk of all those results, we'll have to know exactly when they apply and when they don't apply, right? So they apply to weakly reversible or reversible metrics. And from our definition yesterday, you saw that things, every complex can go, I mean, you can reach from every complex to every other complex. It's like our ergodicity kind of thing. I can go from here to here and here to back, no problem. I can go from here to here. I can't go back immediately, but then I can go back some other way, and that's enough. Okay, so that's one thing. Let's look at our zero range process, right? So, and let's look at it, arbitrarily big, not just 1 or 2, etc. And you'll see it's not a difficult thing to compute there either. So, yeah. So there are many, many variations on our zero range process. Let's look at one that we talked about yesterday. Okay. S1 goes to S2, goes to S3, and it keeps doing that. Sn and Sn goes back to S1. In this particular case, the species and the complexes are the same. Okay, so that was easy. How many complexes do I have here?
N complexes.
Right. N complexes, 1 linkage class. And is it okay? Can you see that the number of the dimension of the stoichiometric subspace is n minus 1? Is that clear or is that not clear?
Yes, it's clear.
This last one just gives me like not an independent vector. Okay. So the deficiency is again 0. So everything that we are going to say is going to apply to that zero range process. For the moment, remember, we are talking of mass action rates. But the zero range process, we know a lot of results even without mass action rates. So I will mention a little bit about what happens if you don't have mass action rates, okay? But from the point of view of chemistry or biology, mass action rates are quite a natural thing to look at. And as I said, Michaelis-Menten or Hill kinetics or all kinds of other more complicated things you can think of as mass action rates with some kind of time scale separation amongst the different reactions. Okay, so what about if I have a zero range process now? So zero range process 1 and then zero.
Supriya, there's a question.
Oh, yeah, on the chat.
If Sn was not going to S1,
Yeah.
number of the subspace dimension should be n only, right?
Correct. So I'm going to show you an example exactly there. So Sn is not going to. Okay, so 2 things. So this example, let me just see if that answers your question. If I have sources and sinks, a source on one side and a sink on the other side. In this case, I have exactly the same number of, I don't have the same number of complexes because remember what I said, the phi was 1 more. I mean, phi is also a complex. It's not a species, but it's a complex. So I have n plus 1. I have L is equal to 1. In this particular case, my dimension of my stoichiometric subspace is n, precisely because if I'm able to get 1 more independent vector out of my. If I didn't have, so maybe your question was also had another aspect to it, and that was that if I didn't have either sources or sinks or that periodic boundary conditions, then I mean, you know, then my system is not weakly reversible or reversible, right? I mean, reversible it's not clearly, but it's not even weakly reversible, right? Everything is going to pile up in the corner eventually.
Thank you. Yeah.
Yeah. So we are interested in things which actually will have, as I said, we are interested in things which are going to have a non-zero concentration eventually in the long time regime. Okay, so nothing is zero, nothing is infinity. Everything is remaining within our finite stoichiometric subspace. Okay, so in case you think that everything is only deficiency zero, let me give you an example that we will use, which is this one. I mean, we will use it, if not today, then tomorrow. Let's see. Yeah, this one maybe. X1. Okay, some kind of birth-death process or whatever. I mean, I can continue like that indefinitely for it up down. So this is reversible in the sense that every reaction is going both ways. Okay. There are three complexes because everything on, you know, one or the other side of the arrow is a complex. There's only one linkage class. But what's the dimension of the stoichiometric subspace? Only one, right? Just one. There's only one species, whatever it might be doing. And you can get that this way. S1 goes to 2S1 or 2S1 goes to S1. It's just one species. So this is a deficiency one network. Okay. And the things we are saying are not going to apply to this, as simple as this looks actually. In this case, it turns out you can actually solve it. But I mean, solvability or not has nothing to do with it. Some of our conclusions are not going to apply. Okay, and we'll see actually. We'll take this example again. We'll see where things go wrong.
So
Okay.
here also, you had a choice of writing additional equation. 3s1 gives 4s1. I mean, why did you stop at 3s1? And
I don't have to. No, I can go to 4s1. I can go to 5s1.
so
What will happen to the deficiency then?
you keep changing, right? With additional.
Absolutely. So it will just keep increasing. For that one, now the deficiency became 3 because the number of complexes is 1, 2, 3, 4, 5.
Okay.
We'll see. We'll take this example again to see.
My point is, this reaction is just describing one particular process, right? In a sense that only something like just birth and death is happening. For that, we have different deficiencies based on the way we are writing equation, right? So that seems
Absolutely.
there is some degeneracy there. I mean, delta can.
There is only one way I can. I mean, so having defined what this delta is, there's only. This is the. I mean, it's unique value it takes for that network, right? So then, what does it mean? Does it make it harder to solve or do something else? Okay, we'll get to that. Okay, but for this network, there's just one value that it can take, right? I mean, if I have specified for you the reactions and I said, okay, I stopped at 6s1, this is what it is, right?
Yeah.
So, yeah. So that's the important thing. This deficiency has a value that is completely unambiguous, and it seems to have only information about the network structure. It's some kind of network quantity, some global, whatever, topological quantity or something, right? It's some global quantity. That's very easy to understand from just looking at the network. And just to show that, maybe let me just try to share this screen if that works, because I have. You can see that? Yeah, I think you can. Yeah. So this was what I showed you yesterday, our, proper definition. The deficiency is whatever, okay, so exactly what we said. C minus L minus S. Now, this was a rather interesting paper, or rather the supplementary material of this paper. So this is what they did for whatever reasons, okay. We don't have to go into the reasons. Just look at the, how big these networks are. Look at this column, number of metabolites, number of reactions. Look at the number of reactions. So they've taken important sort of cycles or sort of sets of reactions in something. Actually, I don't know quite. I think, yeah, in various sort of in various systems. Okay, and don't forget about this first first column. Look at the hugeness of these reactions, and then they've actually calculated the deficiency, which is actually quite big. Okay, not surprisingly. It's not zero by any means. So it's a very big quantity. In this particular case, they were just interested in doing this for something else. Okay, so which we may or may not get into towards the end of this. So it's well, my point in showing this was just that it's an easy thing to calculate. You may not be able to solve those metabolite networks at all for anything, but at least the deficiency is something that's easy to calculate. Okay, so. And this was a theorem that we we are going to try to understand. Okay, what does deficiency zero imply for the dynamics? Because the condition, we'll have plenty of time to look at this theorem again. Okay, so even if you didn't manage to read the whole thing, that's no problem. The main point is the following: that deficiency zero is it seems to be a very simple thing that you can just look more or less. Once you get used to it, you just look at a network and you know what its deficiency is. But it seems to have implication for dynamics, right? So how is that? Okay, so that's exactly what we're going to try to understand. And let's see, stop sharing. Okay. Yes, so this is about 45 minutes in. I mean, so if any of you have any, urgent questions, please feel free to ask and I'll continue. So we are in no hurry. I mean, I can to do everything very fast because we have some time and we'll get through our material anyway. So feel free to ask, okay? But this was more or less sort of revision of what we did, but I just wanted to be sure that we were on the same page. Okay, so the idea is how is delta related to the fixed points? And we saw that, and in fact, related to that is why is delta only, and why can delta only be a non-negative number? Okay, so if I'm writing it as C minus L minus S, it's not completely obvious that it can be only zero or positive, and we'll see that too. So all those things are related. Okay, so let's see how we do this. Okay, maybe, I mean, we can just write down what we did yesterday. For our favorite enzyme kinetics, 4 species, and we had our reaction rate equations. Okay, is there a point in writing them down, or okay, maybe there is. So we are going to take a look at these rate equations even in our tutorial, right? But actually, it turns out in this case, you can solve them very easily just because of the structure. Okay, so yeah, so maybe yeah, so that was, I think, the longest. Let's just do it. So I hope you got a feeling for how we write these rate equations down. You just keep track. You do some bookkeeping and keep track of exactly the information that network is trying to tell you. So we'll take a closer look. So I'm hoping that I'm not making any mistakes here. So you should take a careful look, and we will take a closer look even in the tutorial. Yeah. So if you're looking at the deterministic description of our CRNs, this is basically it. We would like to solve this thing. Okay. Ideally, maybe we would like to even understand time dependence. This is it. This is our full deterministic description of our CRN, if it's that CRN we are talking about, right? This is it. We would like to solve this, maybe the full time dependence, but you know, if you're interested in something like steady state properties, then we are interested in what sort of fixed point does it reach eventually. Does it even reach one? Does it reach one in which all the concentrations, so when I keep saying positive, etc., what I mean is that all these concentrations, XE, XS, XES, and XP, reach some non-zero positive value. So does that happen? How, if that happens, how does it depend on the rate constants? Does it happen for all values of the rate constants, or only some? Okay, so those are some of the questions that you can ask. Does it depend on initial conditions? Okay, so those are some of the questions that you can ask, even if you're only interested in the fixed points. Now, as it turns out, you can solve this set of equations rather easily. I mean, without going through all that, you know, without going through any formalism at all. Okay, and it's a good exercise to go through, just so that we have a second check on what we are going to do, all the shortcuts that I'm going to show you. Okay, so here's a set of equations we are going to take a look at. What did I say yesterday? I said that this you know, bunch of stuff can be very cleanly written, very cleanly and nicely written in the following way. Maybe I'll leave it on this. Right. So basically, all this information is here. Okay, and that's something that you should check. Okay, so herein, you know, because this is in our deterministic description, our rate, you know, the concentrations or fractions of these things is all that matters to us, right? We don't have anything else to worry about. This equation is going to be very important for us. Okay, so we'll keep thinking about it and looking at it. And the fact that we are able to write it like this, you know, is what it's doing is it's sort of highlighting some linear structures in it, which looking at these rate equations is, you know, one would be a bit clueless about. Because on the face of it, you say, oh, I mean, you know, it's got some non-linearities. It's not like, you know, it doesn't look very linear out there. But actually, there is a lot of linear structure behind it. And therein lies, you know, why this theorem works, this deficiency zero theorem. You remember what psi was? Psi was, in our particular case, 1 x e x s. Okay, so I should just be a bit careful that I keep the same order here. X e x s, x e s, x e x. So you can convince yourself. So one of you, I remember, asked yesterday, why do we have a psi like that? The reason is, of course, that these things are, of course, showing up here, right? XE, XS, XES, of course, and XE, XP. Okay, so when you write, when you make this distinction between a Y and a A and a psi of that form, you exactly get back these equations. And the Y, remember, was our containing information about our stoichiometry. So I construct it like this: species on the labeling the rows, complexes labeling the columns, and our usual rule for denoting every complex in terms of the species. The complexes are made of the species, so I should always be able to do this. And then this A matrix, which is some information about the adjacency graph here. It's just telling you, without going into this mass action, like another one of you remarked yesterday, it's just keeping the rate constants. It's the full rates, of course, you get when you multiply by that vector psi. It's just keeping rate constants out here. Okay, and just the form of this matrix, maybe some of you will sort of recognize. It's like a sort of stochastic matrix, but not reducible. I mean, not irreducible, I should say, right? So it has this block structure, and this block structure is exactly related to the two linkage classes. So we'll come back to that. The structure of this thing, everything will play a role. That making sense?
Yes.
Okay, great. Okay, now let me just give you one other sort of interesting fact, which we will use again, okay? Because this there's a lot of structure here, and so all this is linear. This is just some matrix algebra going on, right? So there's a Y and there's a A, everything linear. Then you might say, oh, this psi looks very non-linear, but there is some linearity hidden behind in that psi also. So let's just see how that is, okay? And now I'll have to erase this, but we'll take a look at it again in the tutorial. And the book by John Biles and Jacob Biamonte makes this point rather nicely. So that book actually, is about a lot of other things too. So they're interested a little bit in, formalisms for these kind of processes which look like quantum mechanics. We may mention that towards the end. Okay, but that's just, those are tools, those are formalisms. But the book also talks a little bit about, this theorem in some of the chapters. And I think it's very well explained, and particularly this point. So there's a way to write psi as x to the y. Okay, so that might look very strange to you. So think of this, because x, okay, so in this particular case, think of x as a column vector, sorry, a row vector, which is exactly this. Sorry, not, okay, think of x as the same as our row vector, just the transpose. Okay, so you could ask, how do I take x to the power of a matrix y, right? So x to the y would mean that now I have this matrix y here, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay, and so we just define that this operation means, remember, if I could very nicely multiply x by y, right? That's no problem. But now when we say to the power, we define it in sort of the same way as we would when we were doing the multiplication. The first element here is just xe to this quantity times xs to this quantity times xes to this quantity times xp to that quantity. But of course, all that is 0. So the first element is just 1. And then the second element is just xe to this quantity, xs to this quantity, xes to this quantity, xp to this quantity. That's just xe. So you see where I'm going, right? If I continue this way, I'll get exactly back my column, the psi as a row vector. XE, XS. Okay, so that's just a thing one plays around with and convince yourself that that works. And in particular, what we are going to use, because it's always good to know a little bit, or it's always good to see everything at least 2 times, right? Then you start getting a slight feeling of familiarity. So we're not going to use this right now, but we're going to use it perhaps in tomorrow's lecture. So maybe I don't need to erase this. So basically, I could also write this as log psi is equal to y transpose log x. And now I forgot the x vector there. I mean the same thing, okay? Whenever I say x, then it's typically a column or a row vector. In this particular case, log psi is log of this quantity. What does log of that quantity mean? It's just log of each of the elements there, okay? And then you can convince yourself that this is going to give me back exactly that. Okay, so that seems a bit like magic, but okay, let me just write that down. Y transpose, but we are going to use this later. So Y transpose, remember, I just transposed the whole thing, so that's going to just be, so basically, log of 1 XE XX XE XX. So this is just showing you that there is some structure even in the psi, okay, which is going to be important for us. In fact, it's going to be very important. So that psi, at least the log of it, can be written in this particular way. Okay, I hope I'm not making any mistakes with the transpose, but you can check that this is going to work.
Supriya?
Yes.
Can you show me how you got the first entry in the expression above what you're writing right now? How did you get 1?
This one?
Yeah.
Because, okay, so how did I get 1? The same way I got everything else. It's XE to the first entry 0.
Oh, sorry, power. Yes, okay. Right.
Yeah, so sorry, to the power, yes. Yes, not multiplication, to the power.
All right.
X.
Yes. Okay, thank you.
So you see, every entry works out nicely that way.
Yes, I can see that.
Yeah, great.
That makes sense.
And hopefully, this is going to work out too. Okay, so why don't you try that out? So basically, this is something we are going to use a lot. That the psi, which looked weird and nonlinear, actually also has a hidden structure behind it related to the stoichiometry. And this is going to be very important. So I will actually emphasize it again, but we'll come back to this. Okay. So with that out of the way, let's go back to the rate equation. Okay. So now let's use it, and let's just write everything in short forms. So now I'll just write x where I actually mean a column vector x, dx by dt. Okay, the same thing we've been writing all this time. And now let's write our psi as x to the y. Okay, now that we learned how to do that. Okay, and what are we interested in? We are interested, as I said, not in time dependencies, because that's a harder problem. Okay, maybe we'll mention a little bit about that later, but that's a harder problem. At least we should understand something about at least steady states before we get to time dependencies. So from that motivation, we are only interested in this, right? So these are our fixed points. If we can solve for what is xe at the fixed point, let's call it xe star, xs star, xes star, xp star. That is our fixed point, which we'll call x star. This is what we want. And what will it depend on? Of course, it will depend on those rate constants in some way. Okay, we could, of course, have just gotten down, like sort of pulled up our sleeves and just tried to solve those set of rate equations. And in this particular case, you can do it. Okay, and we will try to do it in the tutorial. But we'll see an easier way to do it. Okay, by looking at this linear structure, by all this matrix multiplication business. Because what is this telling you? So I asked you to think a little bit about this yesterday. If y times a times something, okay, is equal to 0, okay, y and a are matrices. There's only two possibilities this thing can happen. Either this makes the vector psi, which I'm writing as x to the y. Okay, let's for the moment write it back as psi. So this vector psi, either it's lying in the null space of A. Remember what's null space? Okay, so this was, I had to actually brush up some linear algebra too. Maybe many of you will know this much better than me, right? So, and there we are going to use at least two important results from linear algebra. So null space just means that any vector that A puts to 0. Of course, A puts a vector of zeros to 0, but that doesn't count. And if A puts some vector to 0, it puts a sort of scalar multiple of that also to 0, but those are not independent. Again, we are going to be interested somehow in the dimension of the null space of A. Okay, and we'll see that the dimension of the null space of A is actually related to the, remember our A had this block structure. So it's going to be related to the fact that there are two blocks. So it will be like in this particular example, that is, there will be two independent vectors it puts to 0. And you can kind of see what it is. It will just be something in the first 3 elements, all 0 zeros below, or all 0 zeros above and something there. How do we know there are only two? We'll get to that. So either psi lies in the null space of A, or psi does not lie in the null space of A. A passes it through nicely without annihilating it, but Y annihilates it. Okay, so those are the only two possibilities. Just now, that's the only way that I can ever get a fixed point, right? So two possibilities. So A psi 0 implies psi lies in the kernel of A. Okay, so these are, I mean, kernel is just a general word for null space. So, or A psi not equal to 0, but Y times A psi is equal to 0. Implies psi lies in image of A intersecting kernel of Y. Okay. So image of A is just a fancy way of saying whatever A did not kill. So either A kills a vector or it doesn't kill a vector. A can't do much more than that, right? So if it killed the vector, that vector was lying in the null space of A. If it didn't kill a vector, that vector lies in the image of A. And this just means that whatever that vector was that A did not kill, then that lies in the image of A, but that it got killed by Y, so it should be lying in the kernel of Y. Is that making sense? Okay, I'm sure many of you remember your linear algebra much better than I do. At least you've done it much more recently than I have. Okay, so I had to brush up some of these things, and I'm going to use some of these some results from linear algebra without proving them. So those of you interested in proofs should take a look at that because they are very interesting. Okay, so one result that we are going to, was it a question?
Yeah, ma'am. Are these that all two possibilities? Like suppose y times a is a new vector, right? Sorry, new matrix. Like
Y
y
times E is a new matrix, and you should
yeah,
try
it can be
what
the
it is.
null space of that matrix. We can say, is this possibility is included in first two or it can be a
Yes.
new possibility? Like this
So
possibility two you have written.
it is included in the first two. Yes.
Okay,
Because
the
y times A is a vector, y times A is a matrix, and you should check what that matrix is, of course.
Yeah.
That matrix will, of course, only, I mean, so basically this will be the only two possibilities in which way it can annihilate any
Like
vector.
my question is like, can there be any different kernel than kernel of A and kernel of B? Like YA, not B, kernel of Y. Like kernel
Yeah.
of A and kernel of Y. There are two kernels. You are saying
Yeah.
that psi can be either of one of them. Like I'm
Yeah.
saying that can YA have a different kernel which is not a kernel of any individual A or Y? Like, is there any possibility? Like,
No, there is not.
there is
Okay,
not.
so let's get through this a little bit, and maybe it's clear or maybe it's not clear, and then if it's not clear, we should think a little bit more about it. But there is no other possibility.
Okay.
So maybe to understand that, okay, so let me get to this very interesting point. The reason that we went through all this is going that I'm going to give you another definition of this deficiency. Actually, why it's called deficiency, I have no idea. Okay, somebody named it, and that's what it's called. What is it a deficiency of? I don't know. But in any case, that's what it's called. Okay, so now here's a nice another definition. And you see that it's going to be, this explains why it's a non-negative number. Okay, so deficiency is also, and we're going to see, are we going to see it? Yes, we do have time, yes. So we are going to see how this definition is the same as that definition. Okay, we're going to see that. It's the dimension of the space. Okay, so the dimension of the space at best. So what space is this? The space of all such vectors. Of course, I'm thinking of independent vectors, right? I mean, a vector times the same vector multiplied by 10 is not going to give me any new information. So the space of all vectors which lie in the image of A and also in the kernel of Y. Okay, and deficiency 0 then means that there is no such vector. All vectors, so what does that mean? In turn, that means that this second possibility does not exist for deficiency 0. Only the first possibility exists. So deficiency 0 networks, all information is contained in the A matrix. Okay, it's enough if I find the null vector for the A matrix, and then I'm done. Okay, almost done. So that's part of this deficiency 0 theorem. That for deficiency 0 systems, so deficiency 0 networks, this A matrix, this adjacency matrix, which doesn't seem to have any nonlinearities in it at all. So simple as that, if that's the null space of that is guaranteed to give me the correct fixed point. And we'll see why. Okay, because as you see, there's an aspect to this. Why the null space of that is something. How am I guaranteed that it's going to give me a vector like this complicated vector psi? Okay, that's going to be the sort of most non-trivial part of this deficiency 0 theorem. But you see that this this A is rather a simple matrix if all I have to do is find its null space. So I hope that that statement is a bit clear. And let's try now to understand why is that statement and that statement the same thing. Like, okay, so here now we have to use some results from some linear algebra, which I'm not going to prove for you, but those of you interested should definitely look up this proof. Okay, so so we are interested in this. Okay. So now, okay, so let's think of our A, right? Let's continue thinking of our A. Dimension of A is defined as number of columns. And the number of columns or the number of rows here is just our number of complexes C. Okay, so that's where the C is coming in there. So the number of columns is just C, in this case, also the number of rows. Okay, now there is this very interesting theorem in linear algebra called the rank nullity theorem. So I'm going to use this. And what that says is that the nullity, so I think so this theorem, the way that I'm going to phrase it is for finite dimensional vector spaces. So it can be said quite generally for vector spaces, but let's just be a little bit more lowbrow and just think of our matrices. Okay, so nullity A plus rank A is equal to C. And what is nullity A? Nullity A is then the dimension of the kernel of A, and rank A is the dimension of the image of A. Okay, let's take a little example just to make sure that we understand this. So basically, A can do two things. Either it can annihilate a vector, or it can pass it through, okay, and give you a new vector. Okay, basically, it's the only two things that A can do. And this statement is saying that the dimension of the space of vectors that it can annihilate plus the dimension of the space that it does not annihilate can at most be the number of columns. So let's just take a little example. Okay, so maybe this will be clearer in the example. So let's just do it this way. Okay. And you have a very finite amount of space. You have to choose what to keep. So let's take an example here. 1 0 0 1 1 1. Suppose I had a matrix like this, okay? I mean, because this is irrespective of if it's a square matrix or not. So the dimension, so the image of A, that's actually, you might think, okay, how am I ever supposed to know what's the image of A? It acts on something, gives me something else. Like, how am I ever supposed to be able to describe such a thing? But actually, if you think of this matrix or any matrix, and it acts on some column vector, you can see that it's actually, column vector. One can see that it's actually some, so it's going to be some combination of the columns of this thing, okay? So the image of A is usually, we can see, convince yourself that it's the dimension of vector space. Spanned by columns. And the kernel of A, okay, so maybe I should take this example for the kernel of A. You can convince yourself that it's just one vector here, 1 and -1, 1. Okay, maybe that was not a, so let's maybe that was not very clear. So let me explain that a bit more for you. But the kernel of A in this particular case is just something simple, right? It's just the vector that it puts equal to 0. So the kernel of A will just be if this thing is. Is that okay? And the image of A, so this is the kernel, and this is of course not proving any theorem for you, just giving you an example. So kernel. The image of A, you can convince yourself, is actually going to be just some linear combination of 2 independent column vectors. What are the number of independent column vectors here? The number of independent column vectors are just 1, 0, and 0, 1, right? Because 1, 1 is actually just the sort of sum of those two. So the image of A is the dimension of the vector space spanned by the columns. When you say dimension of a vector space, then of course you have to think of independent vectors. So the image of this is just always given by some constant times 1, 0 plus some other constant times 0, 1. So you immediately see that the image has a dimension 2. The kernel has a dimension 1. And of course, this rank nullity theorem is satisfied. Okay, so the image of something is just is actually not a difficult thing to actually, if you give me a matrix, it's not a difficult thing to look at this matrix and see what's the image of this. How many independent column vectors are there? So for example, what's the image of this A? How many independent column vectors are there? You see that you can think of these two, and then this will be some sum of those two. And then you can think of these two, and this will be some sum, whatever. So there are 4. So this matrix has image 4. Dimension of the image space is 4, and dimension of the kernel space then has to be 2, because the number of columns is 6. That making sense? Okay. As I said, I'm not proving this for you. And in fact, I don't think I remembered the proof at all. But it's those of you who are interested should actually look it up, okay? It's an interesting result. Okay, so let's then just in the last bit get to our definition of the deficiency using our rank nullity theorem. So let's get rid of this. So basically all the results here are, first what they're doing is looking and saying that this apparently nonlinear problem has a very linear structure. And then using that linear structure, using all the information that linear structure tells us, right? Okay, so that's basically how the whole theorem was proved. Okay, so yep. Okay, so now we can write this. Okay, so dimension of the kernel of A plus dimension of the image of A is equal to C. Now the dimension of the kernel of A is actually just the number of linkage classes. Okay, like the example that we gave you here. Okay, we'll see a bit more about that a bit later, I guess tomorrow then. The number of linkage classes was 2, right, up there. That translates to 2 blocks. And that translates to 2 independent vectors that puts equal to 0. As I said, it's easy to calculate the image and it's easy to calculate from that the kernel. And we saw that in the other way too, using the rank nullity theorem as well, that the kernel is actually just 2, right? So, and 2 is just the linkage classes. So the dimension of kernel A is L, okay? So far, so good. What about the dimension of image of A? Now I break up this dimension of image of A in 2 separate ways. One of them is that it's the dimension neither, okay, let me write this down. That dimension of image A is also in the image of Y. So it's the dimension of YA, or it's the image A kernel Y is equal to C. And you see now that this is beginning to look like this, where this was what we called okay, so let's just talk around these two last relations. So something is lying in the image of A. So A did not kill it, okay? And then it gets acted on by Y in our rate equation. Okay, so there was the psi. I hope you can see that. Yeah, there it is. There was the psi. It did not get killed by A, and then it got acted on Y. Then there are 2 choices for it. It got killed by Y or it didn't get killed by Y. Okay, so that's what this is saying. The image of A can lead to vectors which are either lie in the dimension of the image of YA itself, or it lies in the image of A, but in the kernel of Y, which means that Y killed it. So if you think of it, that's the only 2 things that could happen to that vector. Okay, so it's the dimension of the image of YA is actually the same as the stoichiometric subspace, because that's the space in which this X is moving around. Okay. Of course, I'm just saying it for you, but you'll have to actually play around a bit to convince yourself that that's the case. Okay, so the dimension of the image of YA is the same as the dimension of the stoichiometric subspace. And the dimension of image A intersection kernel Y is then what we defined as the deficiency. And so you see that we get back this relation. Okay, and then in this way, we also see that deficiency can be 0 or it can be positive, but not a negative number. So basically, so this is another way to look at the deficiency, which is going to be more useful for us, because now what did it tell us? Because just looking at that and then saying that there is going to be fixed points which are unique, etc., seems very mysterious. But now we made one more step. If we look at this and say that if this is 0, then we are getting somewhere. Okay, because what we are saying is that for our deficiency 0 networks such as that one, we are always guaranteed that if I find a solution to A putting some vector to 0, if I find a vector in the null space of A, I'm guaranteed that that is the solution to this equation. That I can massage that vector such that it gives me a psi with all its non-linearities, etc. Okay, so that's where we are heading. But okay, before that, of course, you could say, how am I guaranteed that this A has a null space at all? Maybe maybe it doesn't put anything to 0. Okay. So how am I guaranteed? How do I know how many things are in the null space of A? And for that, we will use yet another relation from a very famous theorem from linear algebra, and that's called the Theron Frobenius. So we will use this theorem to understand something about the null space of A. Okay, and maybe many of you have seen this before or not. But again, it's not something I will prove. Okay, so this is quite an involved, it has many, many aspects to it. We will use it only to the extent that we need to understand our deficiency zero theorem. Again, those of you who are interested should definitely look it up. A very, very important theorem that we use in some sense all the time. But I will not do that now, right? So because my time is up. So let me stop for today. And yes, questions?
I have one.
Yes.
So I just didn't get you mentioned that we should play around ourselves, but with the dimension of the stoichiometry matrix times A would be equal to the stoichiometry subspace. Could you like, why is it that this span of A doesn't matter in this sense? Or maybe it does and I misunderstand.
So, so what I said was that the dimension of the image of YA
yes,
is equal to the stoichiometric subspace. So if you calculate YA, I mean, if you just multiply those matrices and you get a YA out of it, and look at the column vectors, you'd see that those independent column vectors are exactly going to be our reaction vectors that we got.
Right. So maybe I just misunderstood that the stoichiometry subspace is not only the subspace of Y, it's the subspace of Y and A.
Yes, the image of Y, correct, yes.
Yeah, okay, yes. Okay.
Yeah, absolutely, absolutely. The stoichiometric subspace is the space where my concentrations are moving around, right, and reaching fixed points. It could either have the dimension of the number of species, it could, or if I have conserved quantities, it has a lower dimension. It's all the stuff that we discussed. But if you, so why don't you play around, take this Y and take that A and multiply them, and you get a matrix out of it, and look at the column vectors. And you'll see that those column vectors are actually, there will be 4 independent column vectors. They will be exactly the 4 related to the reaction vectors that we got there.
All right. Yes.
Yeah.
So I mean, Supriya, so you said the fixed point is going to be sort of, I mean, if delta is 0, then it's going to be the eigenstate of A. Is that right?
With the 0 eigenvalue.
With 0 eigenvalue. So in this case, it looks like there are 2 such eigenvectors.
But we will build a unique one out of those. We
No,
will build. So there are 2 such eigenvectors, correct? Because there are 2 linkage classes. But out of that, we will build a unique psi. We will see.
Oh, there's going to be a unique psi.
Yeah. And you can only do that. So I wanted to take an example, but maybe we'll do that tomorrow.
Okay.
No point rushing now. If you don't have deficiency 0, then also, I mean, nothing is stopping me. I can go and find an eigenvector of that with eigenvalue 0. But I'm never going to be able to build a psi with that.
So if the deficiency is not 0, then this 0 eigenvector is not going to give you the fixed point, is it?
No, absolutely. Yeah. Because every reaction network is going to have an A matrix like that.
Right, yeah, okay.
I mean, nothing is stopping me from finding the 0 eigenvector. It's always going to have some kind of 0 eigenvector, but it's not going to give me psi.
Okay, so the next stage is from the 0 eigenvector. Okay, so how to construct X? That is the next step, is it?
That is the next stage, and that is the last step in our understanding the deficiency. Yes, absolutely. And that's I think, the most non-trivial part of this thing. I mean, sort of. Again, we'll need a little bit more, rules about kernels and images, etc. for that.
Okay.
But the idea is not very difficult. We'll do that tomorrow.
So the other question was, I mean, you are talking of chemical networks, but this analysis is basically valid for any set of ODs, right? Isn't that like which have, like, let's say integer?
Sorry, what did you say, Abhishek? You got cut off.
No, I mean any set of ODs which doesn't have, like, let's say, I mean, which are in polynomial, which involves us polynomials, this analysis should still be valid, right?
Yeah, so I mean, anything that, it doesn't have to be chemistry, anything that can be written sort of, precise, exactly, like our zero range process, for example.
Right, okay.
Exactly, yeah. So it's actually a very general result. I mean, that being said, you could say that, if you're looking at very interesting behavior like strange attractors or stuff like that, then of course it's not deficiency zero. So that much one can say. Any system which has multiple fixed points or extinctions or absorbing states or strange attractors or whatever is not deficiency zero. That much one can say also.
Okay. Okay.
So we can discuss all this more stuff also in the tutorials. I mean, we can keep it a bit free because I'm not sure that what I suggested is actually going to take 45 minutes. I mean, I have a full 45 minutes today or what?
Yeah, so you can take like whatever time. I mean, so
yeah.
I think Vijay is going to take the first 45 minutes, so 6 to 6:45, and then you can do the.
Okay.
Yeah.
Okay,
so for
I'll just connect back on here. Yeah.
Right. Okay. Yeah. So just, I mean, information for others. I mean, so Supriya's lecture notes and a tutorial is available on the website. And yes, that's.
Well, the lecture note from yesterday, and it's just handwritten notes. Okay, I'm sorry. I mean, I'm just running out of time here, so I haven't typed them in or something.
Right. Yeah.
But I hope it's just it's understandable, and I hope it gives you a way to delve a bit deeper into this.
Right. Yeah. Okay. So so we'll break now and meet again at 6. Yeah.
Yeah. Let's do that.
Yeah. See you tomorrow.
See you.
Yeah, bye.